So, having explored the lattice enthalpy, the energy required to form a crystal, we're now going to look at the energy required to break it up again, the enthalpy change of solution. So the energy change associated with the dissolving process, and we're talking something like an ionic lattice going into solution, that is called the enthalpy change of solution. And we represent it with the notation that it's delta subscript sol for solution, and then H for enthalpy, and then the symbol for standard conditions, the little underground symbol. Now, what we basically mean here, and using sodium chloride as an example, is we have a sodium chloride crystal and we are disrupting it to make its ions float separately from each other and become completely surrounded by water molecules. This particular reaction has an enthalpy change of plus 4 kilojoules per mole. So how could we measure such a thing? Well, we would measure the heat given off or taken in when we dissolve some of these crystals into a solvent like water. So here is an example calculation. It's for potassium chloride, and you can see a certain piece of information given. The volume of water, how much water is going to get hot, basically, or cool down, and the mass of the potassium chloride that's been added, and there is the initial and final temperature of the water. Now our approach here is we first must calculate the amount of energy change that must have occurred to raise the water by that temperature. So let's have a look at a work through of this calculation. So the first things first, we are going to take the known density of water, 1 gram per centimetre cubed, and we're going to use that with the volume to find the mass. So we know that the density is the mass divided by the volume, so the density times the volume would give the mass, and so therefore 1 times 25 is 25 grams. There we go, that's the mass of the water. But it's very important to realise that it's not just the water that's being heated, so is the crystal itself, and we must add to the mass of the water the mass of the ionic compound. And so in this example, because the mass of the potassium chloride was 7.46, we need to add that to 25 to give a total mass of substance that is heating up or cooling down as 32.46 grams. Next, we're going to use this in the formula Q equals mc delta theta. So 32.46 is the mass multiplied by the specific heat capacity of water. Yes, that is going to be changed slightly by the presence of the potassium chloride, but not a lot, and so it's a good approximation for now, multiplied by the temperature change, which is 11.4, and it gives minus 1.56 kilojoules. But that was not for 1 mole. We need to know how many moles of potassium chloride went into this. So the second stage is to work out how many moles. And we do that by taking the sample mass of 7.46 grams and dividing it by the molar mass of potassium chloride, 74.6. It means in our sample we have 0.1 moles of potassium chloride. And because the enthalpy of solution is going to be the energy change divided by the number of moles that we have to work out the energy per unit mole. 1.56 divided by 0.1 gives that, and so the enthalpy of solution is minus 15.6 kilojoules per mole, and that is how you calculate it. So what exactly is this energy doing? Well, in the disruption of that crystal and taking it into solution, actually that energy is doing 2 things. It's a 2-step process. The very first thing is those sodium chloride ions that are attractive to each other need to be physically pulled apart, and that takes energy. The second thing is once separated, they must be then surrounded by water molecules. Because of the polar nature of water, the negative oxygen molecule within the polarity of the actual water molecule is going to be turned to face the positive sodium ion. And by the same way, the negative chloride ion is going to be closest to the more positive hydrogen atoms on the water molecule. Now this orientation, this rotation of all of the water molecules around the ions is going to take a little bit of energy also. And so we call that the enthalpy change of hydration, and that's going to appear in our energy diagrams shortly. And so here it is in its most primitive form. We are going to adapt this, but for the sake of explanation, let's start simple. We have the undissolved lattice at the bottom, and what's happening here is it is going to turn into aqueous ions. Now, if you follow on the left-hand side, immediately above the ionic lattice, the bottom, so go up the left-hand side as we're looking at it here, you go past the enthalpy of solution. The next line up is where the aqueous ions are, the sodium plus and the Cl minus. And so for this particular chemical, it has risen in energy just a small amount. This endothermic reaction that has taken in energy and then raised. It's actually very close, that being in solution has almost the same energy as being in a lattice. There's not a lot of difference in this particular example. But if we look at what else is going on here, if we consider how much energy it would take for them not to be in solution, but for them to evaporate, for them to become gaseous, basically for them to escape the water, then you can see there are two enthalpies of hydration, one for the chlorine, which is 378, and one for the sodium, which is 406. Both of those energies must be paid into the chemical to raise the chemical in energy so that both of those ions are now in a gaseous form, which takes us to the very top. Now at the top, you could have this go all the way back down, or we could measure the difference between the gaseous ions and the ionic lattice by the lattice enthalpy that we spoke about in the previous presentation. That lattice enthalpy spans the entire gap from the top to the bottom. Now you guessed it, these Born-Haber cycles work by knowing all of the parts of the picture apart from one missing energy, and we're going to apply Hess's law shortly. So remember, for Hess's law, there are, between any two places, there are two routes that we could get there. And they must, in the end, equal the same. And it doesn't matter from where or to where. So if we were looking at the significant point, the place where these are aqueous ions, when it has dissolved, going from gaseous ions down to aqueous ions through route 1 or route 2 is ultimately going to take the same energy change. How could that be if route 2 is a smaller arrow than route 1? Well, route 1 is going further, but it's coming back some. In order for it to get to the same length that route 2 has, it is by definition going to be the same size arrow. The energies are going to be equal. So dividing up the journey, A, the lattice enthalpy, and D, the enthalpy of solution, those two added together would have to be equal the two enthalpies of hydration for the sodium and the chloride ions respectively. This enables us to write out this formula. It's quite complicated when you write it out, but actually if we put in the values, we know that if we were, say, for example, interested in the lattice enthalpy, and we knew everything else, then we could work it out, because we know the two enthalpies of hydration was minus 406 and minus 378, and we know the enthalpy of solution is plus 4. It's very important that we get the negatives and the pluses the right way around. We're adding them together, but subtracting from B and C, D, to get A. So it's always worthwhile taking it back to that original formula to make sure that your positives and negatives are acting in the right direction. So we see we get an answer that it was minus 788. So whereas it gave out energy, it was exothermic in forming the lattice, it is actually endothermic when it dissolves back into water again. That plus 4 kilojoules per mole is how much energy needs to go in to raise the temperature and to raise the energy of the sodium chloride into its ions. Now we see this all the time, don't we? Because we see people putting grit or rock salt on the roads. And what happens is the salt is dissolved into the water and it helps to stop it from freezing. But why? Well, the first reason is called the colligative effect. And it's what happens when those salt ions have dissolved in the water is that the water molecules try to present the opposite charged surfaces of their polar molecules towards those ions, and it prevents the hexagons of water ice from forming. Now, the second thing that almost acts in the opposite direction to this is that endothermic dissolution, heat being pulled from the environment into the solution to make to allow the dissolving to occur. Now, this is basically having the effect of lowering the temperature of the environment around this water ice, and that is going to result in more freezing. So the two effects actually work opposite to each other, but the colligative effect tends to win, and it causes a net lowering of the freezing point. You may have seen this in other forms. You can even make ice cream with it. So if you get some ice cream mixture and put it in a bowl, and sink that bowl in another bowl of ice, and you sprinkle salt on that ice, what happens is that salt gets dissolved. It pulls heat into the ice from the surroundings, and pulling the heat out of the ice cream mixture enables the ice cream mixture to freeze. So that effect that we've basically just observed in that last Born-Haber cycle is the reason why we can make ice cream without a refrigerator using just ice and salt. Now, isn't that interesting? Being able to pull heat out of the immediate environment can be quite useful. You might have seen these ice packs used for injury or when you're not feeling very well. They are basically a crystal like the sodium chloride, which is endothermic when added to water. So basically its dissolving process sucks heat in from the outside world. But though salt is not very good at this, it doesn't suck in very much heat, some other crystals do. Ammonium nitrate is a very good one. In fact, urea, if dried out and crystallized, would draw in a lot of heat if we added it back to water once more. And so the way they do it is there's a pocket of water inside the ice pack and these ammonium nitrate crystals. When the pocket of water is popped, it starts to dissolve the crystals. It's an endothermic process. It draws in heat from your hot head, and that is what makes you feel better. Now, this process is beautifully simple for sodium chloride because it's just one sodium and one chloride. But of course, if we had an ionic lattice made from something, say, in group 2, then things are going to get a little bit more complicated. Because not only do we have differences, they actually affect what the diagram looks like. So something like calcium bromide. Being in group 2, calcium is going to bond with 2 bromide ions. And that means that we're going to have twice the amount of energy coming from that hydration of the bromide, because there's two ions that need to be hydrated. So we have to count that energy twice, and you can see that is the place on the diagram where we're going to have to count it twice. In this case, this particular reaction is exothermic. So how do we draw it exothermic? We don't draw it going the other way because that would change things. We would have to draw the arrow, rather than going up from the ionic lattice at the bottom, we'd have to draw it coming down from it to lower than it. But of course that would disrupt our entire diagram. So instead what we do is we move the enthalpy change of solution to the right hand side so that we can actually see that having lost the energy, it then goes down to the ionic lattice, and that gets the arrows pointing the right way. Let's see that as a proper example, and you will be able to understand what I'm saying. So here we go then. We have the aqueous ions now at the bottom. They have the lowest energy. The ionic lattice doesn't have the lowest energy, so that actually sits slightly higher up in this energy diagram. There it is on the right hand side. Okay, so let's go from the bottom and work around, and we'll explain what all of the parts of this is. So starting bottom left, we've got two of those enthalpies of hydration, the energy required to make the bromide ions go into solution. And because there's two, we have to have times 2 at the start. Notice I'm not saying kilojoules per mole because it becomes a little bit more complicated. That is how much, not per mole, but per just how much in total based on the fact that there are 2 bromide ions going into solution from every one of these dissociations. Now the second, we've got the calcium above it, the enthalpy of hydration, that is fairly straightforward, and we have the gaseous ions at the top. Now still, the difference between the energy of the gaseous ions and the ionic lattice is the lattice enthalpy, so that I've drawn it again on the right hand side. And that goes down to and touches where the ionic lattice is. Now from that point you actually get a net outflow of energy when the lattice breaks into solution. So from going from the ionic lattice to turning into solution, the net outflow of energy means that the solution must be at lower energy than the lattice itself. So we've had to draw the solution at the bottom. An important thing to think about is it doesn't matter if we draw the lattice enthalpy and the enthalpy of solution on the right hand side here or on the left hand side. It actually doesn't matter at all. It's the same journey between a high energy state and low energy state. You may see that there is a slight convention where we would draw in this, the dissolving, a diagram that contains the lattice enthalpy and the enthalpy of solution, that we tend to actually draw those on the left hand side, so the opposite way around to this diagram. But nobody can tell me why, and nobody can tell me that this is wrong, because no one's quite sure why that convention has started. But you might see this diagram as a mirror image, with the stuff on the right on the left, and the stuff on the left on the right. So that is a complete diagram. We can apply Hess's law, and we realise that A plus D is going to equal B plus C. And so what we can do is we can now solve for the missing enthalpy. In this case, I've solved it for A, but it's not actually very likely. You might actually be able to work out A from the first part of the process. You might already know that, and you might instead be interested in the enthalpy change of solution. That's fine, you could do that. You just need the other 3 pieces of information and then solve it, like you can see here. What could we use this for? In the same way that we could use the endothermic reactions for those ice packs, we could actually use a reaction like this to produce an exothermic reaction and give off heat. Now, we could. There are just better exothermic reactions out there, such as the oxidation of iron in the presence of oxygen and salt. And so this is the chemical that tends to be present in the heat pads that are used for things like menstrual cramps and those sorts of things. So what happens here is there is iron and there is some oxygen, salt and water, and you break it and it gets really, really hot. The same process is used in self-cooking food packets. There is a sachet that contains the food and a sachet that breaks, which contains the exothermic reaction, heating it up and making it all nice and warm. But most fun are those reusable hot packs that you might hold in your hands. They're very interesting really because they do work via this mechanism. They go into crystal form and they come out of a crystal form. So it's sodium acetate and it crystallizes, giving out heat. It's exothermic when it forms a crystal and it's endothermic when the crystal dissolves. So what we can do is we can dissolve it by putting energy in. It means once this is crystallized, we can put it in hot water and it will turn back to a liquid to be used later. The little metal disc inside is just enough to give it the activation energy required to start off that exothermic reaction in the first place.